Hello and welcome. If you're revising for your GCSE Physics exam, you are in exactly the right place. We're going to do a super focused run-through of magnetism, hitting everything you need from the AQA specification, that's section 4.7.1, to make sure you're ready for those exam questions. So let's get right into it.
So here's our game plan. Think of this as your examiner's checklist for magnetism. We're going to tick off magnetic poles, the difference between permanent and induced magnets, get our heads around magnetic fields, learn how to plot them, and finish up with the Earth's own magnetic field. By the end, you'll have everything covered.
Okay, before we dive deep into magnets, let's do a quick warm-up. What actually is a non-contact force? Just have a quick think. It's any force that can act on an object without actually touching it, right? And magnetism is one of the classic examples, along with things like gravity and static electricity. Right, first up on our checklist, magnetic poles. This is the absolute bedrock of this topic. Everything else we talk about is built on this one simple idea, and it's all about where the magnet's force is the strongest. So here's the official definition you need to know. The poles of a magnet are simply the spots on it where the magnetic forces are concentrated, where they're at their most powerful. If you've ever snapped two magnets together, you felt the poles doing their thing. It's as simple as that. And this leads us to the two golden rules of magnetism. You've probably heard this before, but it is absolutely vital. Like poles, so a north facing a north or a south facing a south, will always push away from each other. They repel. But unlike poles, or opposites, a north and a south will always pull together. They attract. Easy to remember.
Okay, we've got the poles, we've got the rules. Now let's look at the two main types of magnets you'll be asked about, permanent and induced. Nailing the difference between these two is a massive tick on that examiner's checklist.
This table lays it all out. On one hand, you have a permanent magnet. Think of a fridge magnet. It's always magnetic, it creates its own field, and it can attract and repel. But an induced magnet, like a paperclip you pick up with a magnet, is different. It only becomes a magnet while it's in another magnetic field. And here is the absolute key point. Induced magnets only ever attract. Plus, the effect is temporary. Take the paperclip away from the permanent magnet, and poof, its magnetism is pretty much gone. All right, so we've been talking a lot about the magnets themselves, but what about the space around them? That's where magnetic fields come in. This is that invisible force field where all the action happens. So the official AQA definition is that a magnetic field is the region around a magnet where another magnet or a magnetic material would feel a force. And you do need to know those specific magnetic materials: iron, steel, cobalt, and nickel. So if you bring a bit of iron into that field, it's going to feel a push or a pull. Now, this is one of those simple rules you just have to burn into your brain, especially for drawing diagrams in the exam. Magnetic field lines always go from the North Pole to the South Pole. The arrows on the lines must point away from north and towards south. Every single time. No exceptions. And if you're wondering why the field lines go from north to south, this quote from the spec explains it perfectly. So what does that actually mean? Well, just imagine you had a tiny theoretical North Pole all on its own. If you put it in a magnetic field, the direction it would get pushed is the direction of the field line. And since likes repel, the big North Pole pushes our tiny North Pole away, straight towards the South Pole.
Okay, moving on to number 4. It's not enough just to know what a magnetic field is. The examiners expect you to be able to describe how to actually plot one out. This is a key practical skill, so let's walk through how it's done.
Here's the method, step by step. You pop your magnet on a piece of paper. Then you place a small plotting compass right next to one of the poles, let's say the North Pole. The compass needle, which is just a tiny magnet itself, will line up with the field. You make a little pencil dot at the tip of the needle. Then you pick up the compass and move it so the base of the compass is now on the dot you just drew. Mark the new position of the needle tip. You just keep doing that, and you'll find your dots join up to trace out a perfect magnetic field line. And for our final section, we're going big. We're scaling up from a little bar magnet on a desk to the biggest magnet you know, our own planet, Earth. You know, the simple fact that a compass actually works is all the proof you need. That little needle spinning around isn't magic, it's a tiny magnet, and it's lining itself up with a gigantic magnetic field, the one that our whole planet is generating. So, what can we figure out just from watching a compass? Well, number 1, it tells us the Earth has a magnetic field.
Number 2, it tells us that field is strong enough to actually move and align another magnet. And number 3, and this is the big conclusion for your exam, it gives us strong evidence that the core of our planet must be magnetic. That's the key takeaway AQA wants you to understand.
All right, to wrap things up and really test your understanding, here's a final challenge for you. We said that an induced magnet, like that paperclip, always feels a force of attraction. Why? Think back to the rules of poles. If you bring a strong north pole near a paperclip, what kind of pole does it induce in the end of the paperclip closest to it? If you can answer that, you have absolutely nailed these concepts. Thanks for joining me for this revision explainer, and good luck in your exam.